All right, we're going to talk about vectors and how we can treat complex numbers as vectors. We're going to add, subtract, and do scalar multiples of vectors. We're going to do this analytically and also graphically, and we're going to show them both ways. We're going to represent vectors as the sum of scalar multiples of unit vectors, and then we get to perform arithmetic operations on vectors using vector representation. So, just so you know, vectors have to be written with angle brackets rather than parentheses because they're not plotted points. They're vectors. They're lines that, have direction. So, we're not going to use parentheses for vectors. We're going to use angle brackets. So, we're going to draw the following vectors. It's really important that we start each new vector at the end of the previous one. So the first one is negative 3, 4, which is kind of easy to find, right? We start at the origin, negative 3, 4, and then we draw our array going to that point. But when we do 2, comma, negative 6, we start from here. We start from the terminal point. We start right here, so we're going to go 2, 1, 2, and then we're going to go to negative 6, 1, 2, 3, 4, 5, 6. And so we're going to connect our terminal point to this new initial point here. And that's our 2, negative 6. And we have 5, negative 4, negative 7, 3. And so our final vector, which is actually negative 3, 1, 2, 3, comma 5, is drawn from the origin, so from here, to the terminal point of the fourth vector. And that gives us the sum of the first 4 vectors. So this vector in green right here, this 3, comma, negative 5, that is called the resultant vector. That's what you get once you add all other vectors together. So I'm sorry, these arrows, those are supposed to be those angle brackets. Just so y'all know that those came out weird. Those are supposed to be angle brackets there. That's a vector, negative 3, 5. So the vector negative 3, comma 4 plus the vector 2, comma, negative 6 plus 5, 4 plus negative 7, 3, those result in the resultant vector negative 3, comma 5. So the sum of 2 vectors, which is the resultant vector, can be shown in 2 ways. First, we do what we did before. The initial point of the second vector is placed at the terminal point of the first vector. The other way to show the resultant vector is we put both initial points at the same point, at the origin. And the resultant vector is the diagonal of the parallelogram that it creates. So let's take a look at that. Okay, so the initial point of the second vector is placed at the terminal point of the first. We did that, right? The other way to do it is to put the initial points at the same point from the origin, right? And then it's going to create a parallelogram, and the diagonal of that parallelogram is our resultant vector. So just so you know, we can subtract vectors just as we add them. You just have to remember that subtraction is actually adding. It's just adding the opposite. So as long as you remember that subtraction is actually defined with addition, with adding the opposite, you can do also vector subtraction. You can stretch or shrink the length of the vector without changing direction if you multiply a constant. So when you multiply a vector by a constant, which in this case we're going to call the scalar, it's called scalar multiplication. So what that looks like is if, you have your vector AB here. Oh. You have your vector AB here, and we're going to multiply it by the scalar k. And what happens is that k kind of gets distributed, it becomes vector k times A times KB. So, and next thing I want to talk about is a unit vector. A unit vector has a length of 1, and the most common are 1, 0, and 0, 1. Ooh, again, these arrows, those are supposed to be angle brackets. For some reason, they're turning up as arrows, but those are supposed to be angle vectors. Angle brackets. These are vectors here, right? So these vectors are represented by I and J. I is your horizontal vector and J is your vertical vector. So I is the vector 1, 0 because that's the horizontal vector. That's over 1, but not up or down because of the 0. So you have a horizontal vector. Whereas J is the vertical vector because the 0 means you're not going to go left or right, but the 1 means you're going to go up 1. So we have a vertical vector for J. So instead of having to write over and over and over again, bracket 1, 0, bracket 0, 1, bracket, we can now use the letters I and J to represent horizontal vector and vertical vector. So each vector can be broken down. Another word for that is decomposed into horizontal and vertical components. So let's look at the vector 4 plus 7i. So here's that vector. It can be broken down because 4 plus 7i corresponds to the vector 4, 7, okay? Which means that 4 is your horizontal, so that's 4i, and 7 is your vertical, which is 7j, right? Because the I represents the horizontal and J represents the vertical when you're talking about decomposing. Okay, so if you want just like a general formula, like, well, how do I know how to decompose? You can use this kind of formula. Complex number is in the form of a plus bi, where the a is the real part and the b is the imaginary. It turns into a vector, a comma b, right? So if you want to break it down into the sum of scalar products of the unit vectors, well, your a, the real part, is just a times the horizontal vector, 1, 0. And your b, the imaginary part, is b times the vertical vector, 0, 1. But we know that 1, 0 and 0, 1, 1, 0 is represented by an I, and 0, 1 is represented by a J. So that's how we get AI plus BJ for our sum of the scalar products of two unit vectors. All right, go ahead and try 2 through 6 evens.